started. Let me shift to the right class. Okay, and problem 1.
Did you start the recording?
I just did. Thank you for checking. And practice quiz number 1. If f of 3 is 5, f prime of 3 is negative 2, estimate f of 3.1. Okay, 30 seconds more. So I'll draw a picture. We know that when the input is 3, the output is 5. It passes through this point. We know it passes through this point with a negative 2 slope. So it might be going something like this, through there. Now, if it was a slope of negative 1, then when it went to the right 0.1, it would go down 0.1. But since it's a slope of negative 2, when it goes to the right, now let's blow this up a little bit. When it goes to the right 0.1, it's got to go down twice that. Because the ratio of the y to the x, change in y to the change in x, is negative 2. So it's going to be 5 minus 0.2, which is 4.8. Okay, and absence of any other information. If you're to estimate f of something a little bit after, it's kind of like trying to look into the future. You have the data up to the present and you're trying to guess what's going to be the case next year. Absence of any other information, you just say, well, this current value, it'll stay where it is. But we knew that its recent trend was going down, and every time we went to the right one, it would go down 2, so we use that information to get a better estimate. And give me feedback on number 1. Was this good review, unneeded review, etc. Type that up, and then hit enter. Great. And I'm getting maybe Avinash, your mic needs to be muted. Okay. Let's come back. Number 2. At time t equals 0, you start with 3 bacteria. After 18 minutes, there are 6 bacteria. How many bacteria will there be at time t equals 24 hours? Also state the instantaneous growth rate. Give another minute. Okay, so we'll start any application problem that we're going to model. You have to know what kind of growth rate. If it's a linear growth rate, use y equals mx plus b. But this one, we know since it's a population growing, that it's exponential. So we use the exponential growth y equals, the model is, now there's two basic models, e to the kt or y equals y0, and then you can use, now we know that we found its doubling time is 18 minutes. So since it's doubling every so often, a natural base might be 2 to the kt power. Either one of these would be fine. We have our preference to e because of the way calculus works. As if the base is e, we don't have, when we take its derivative, we don't have that penalty factor. Also, when you use base e, you get an instantaneous growth rate. And only when you use base e do you get that instantaneous growth rate, and that'll be the constant k. So in either case, the y0 is 3. Okay, and then we know, if we were making a little table of values, at time 0, it is 3 bacteria. Now, there's a mismatch. There's minutes and then hours. I think I want to put everything in hours. Since 24 is such a big number. So we'll say that this is 18/60ths of an hour. In 18/60ths of an hour, there's going to be 6 bacteria. And we can plug this in. You see, you plug t equals 0 in, it turns all this into a 1. And that tells you that the y0 must have been 3. This tells us that y0 is 3. The next piece of data is what we're going to use to find k. So we substitute 6 in. That's in for the t, and then the k is here. And if we did it over here, y equals 3, well, not y, 6 equals 3 times 2 to the, and the t 18/60ths times, that's the t, so then times k, we'll put the k back here. Okay. And okay. Then if we're over here and we solve this for k, we take the ln of both sides. (18/60) divided by 2 is the same as 9/30 k. And
Mr. Shankin, where did the E go? Because
thank you
it's
very much.
E to the KT.
Yes. I lost my E. That was going to be a problem. All right. This is 3e to that. Divide both sides by 2. Do that first. And the same thing over here. Divide both sides by 3. And so I don't want this. And I get 2 e to the 9/30 k. 2 equals 2 to 9/30 times k. And then let's insert some space. Now I'm going to take the ln on both sides. And if we stick an ln here, stick an ln here. Over here, this is a 1 right here. You can just compare the exponents. So this is going to come out in front. ln 2 equals 9/30 times k ln e. This asks e to what power is e, and that's 1. So then k multiplied by a reciprocal of 9/30 is 30/9 times ln 2. And if I punch that out on my calculator, 30 divided by 9 times ln 2. I get k is 2.31, and so on. And I wouldn't use this number when I plug it back in. I'd use all the digits my calculator will give me. So this is an approximate. Okay. And when I take this one, I can just compare. 1 has got to be the same as 9/30 times k, so multiply by the reciprocal. K is 30 over 9. And then, how many bacteria will there be in 24 hours? Also state the instantaneous growth rate. The instantaneous growth rate only comes from this one, when the base was E, 2.31. So 200, now that growth rate is, yes, it's 231% growth rate, instantaneous. Or do you, okay, and then when t is equal to 24, so now let's go back to the modeling equation for both. Modeling equations. This one is y equals 3 e to the 30 over 9 ln 2 times t, and this one is y equals 3 times 2 to the 30 over 9. And when we plug in 24, for the t's, we get our final answer. And then, so I'm going to raise e to that power, I get a huge number, times 3, I get y equals 3.6 something something times 10 to the 24th. And over here, when I plug it in, I'm going to get 2 raised to the I get exactly the same thing. They both lead me to this exact same answer. And what that number is, if I write it out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Look at all those zeros. I have to put a 0 in all those spots. It is a gigantic number. And this is a very typical bacterial growth rate, too. Like doubling in like 18 minutes. That's not a problem for many bacteria. And you can see how unchecked with exponential growth rate, there would be so many. It's we have to have a, we call it a carrying capacity of an environment, or we have other things going on in our body. The white blood cells also catch up and fight off these things, etc. All right, so a little feedback. Number 2 was that needed review, not needed, etc. And go ahead and hit enter. And there's supposed to be E times 3. E times 3, Tristan. We got the 3, we divided it out right here and turned it into the 2. Maybe that's what you were talking about?
No, I think it was just when you dropped the E in the equation. I think that's what
when I screwed up earlier. Okay, gotcha. All right. Please do number 3 now. Let me check back on the feedback on the last one. Right. Most are pretty good with those. Okay, so think carefully about the solution you get when you're done with this problem. See if you can explain the solution. $30 seconds. Alright, so x to the negative 4 dx. And the integral of x to the negative 4 is you add 1, so it's x to the negative 3 over negative 3. From negative 1 to 2. When we put in 2, you get 2 to the negative 3 minus, when you put in negative 1, to the negative 3. And this is equal to negative 1/3, and that's 1/8. This is going to be negative 1 still, 1 divided by negative 1. And the two negatives cancel out, plus 1. So it's negative 1/3 times 9/8. The 3's reduce. And you get negative 3/8. Alright. Is everybody comfortable with this answer? Or is anybody uncomfortable with that answer? It's an open question, anybody to answer. I'll give you a hint. You should be uncomfortable with that answer. It doesn't make sense. Does anybody see why that doesn't make sense?
Well, if you graph that function, it's got a lot, it's like always above the x-axis.
Correct. If you take y equals 1 over x to the 4th, it's never negative. And from negative 1 to 1, 2, this is never negative. So this cannot possibly be the correct answer. But yet we did everything just like you're supposed to. Can anybody explain why this is giving us a wrong answer? Yes.
Because the function doesn't exist at 0.
And what's happening at 0?
The function equals 1 over 0, which can exist.
And what happens is we get really, really close to 0.
It goes to infinity.
Very good. So when x is like 1/1,000,000th, 1/1,000,000th to the 4th power is really, really, really small. And then 1 over that is really, 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 really big. And now, when x is -1, this is going to be +1. But it's going to go up to infinity. And then when x is 2, this is going to be quite small. This also goes up to infinity. And so the reason why this is nonsense, totally bad answer. And why is it? Because we integrated across a vertical asymptote. When you integrate across a vertical asymptote and you don't take into account that you've integrated across a vertical asymptote, you will get something that is nonsense as a result. It pretends to be the right result. Computations work on X, but it's totally inaccurate. All right. When we were doing the partial fraction decomposition problems, and I had to make some up, and whenever there was an integral, and it was x minus 2, x plus 1, I had to make sure that I didn't go from here to here across 2 or across -1. I could have done this one from like 3 to 4, and I'd have been safe. But if I was highly aware of this when I was making up problems for this partial fraction decomposition, because this kind of issue can be happening. And it's something that you all haven't had to pay any attention to up until now. And now that we go over it, you're going to have to really pay attention from now on. Is if your variable's ever in your denominator that you're integrating, then you have got to be very careful. Now, we're going to find out we can actually integrate with vertical asymptotes, but we can't just go right across them. There's a specific way we got to do it, and that's what we're going to get into today. And all right, so number 4, list all the ways that we know how to integrate a function. And if there's a formal name for it, put the formal name in. Okay, now go to your group chat and type in the ways that you've come up with, and then look to see if there's other ways that you hadn't thought of. Okay, group 3. Name at least one way to integrate a function.
We can use just the power rule.
The power rule. Great. Okay, now anybody else, add on. What's another way to integrate a function besides the power rule?
U substitution.
U substitution. What else?
Partial fractions,
Partial fractions.
long division,
Reduce it by long division first, and then integrate it. Good point.
and
What
parts
else?
by integration.
Integration by parts. Anything else?
Logarithmic.
Couldn't understand that. We got almost all of them then? There's known ones, generally speaking. The integration rules, basic ones, come from differentiation rules. So we know how to integrate secant squared, but secant, it's not so easy. So it's just reversing the normal derivative rules. But the specialty ones that we've been going over lately, you can see it on our list to the right. Integration by parts, partial fractions are the two big ones. All right, now questions. Any questions on homework or anything else? Number 33 and 24. Okay. So, number 8.7. Number 33. And are you still getting buzzing as I'm doing the document camera?
Yeah, a little bit.
Is it less though? A lot less than before?
Yeah, it's a little less.
A little less. All right. So let's start with 33. This is the right problem, correct? For
Yes.
Yes.
okay. And all right. So I went to the company and got a specific driver for them for this document camera, but it still has some buzzing, so I'll have to contact the company. All right, so this one. there's lots of rules. Integration rules for x squared stuff. And the x squared stuff, and especially in the denominator, occurs very often in applications because we have inverse square laws in physics. So we get all kinds of integrals when you're starting to apply math to real situations. You get this kind of situation fairly often. But the back of the book doesn't have this middle term. That's the problem there. So we've got to rewrite this. And then we push the 10 over to the side. And then we're going to add and subtract something. The perfect trinomial square needs to have half of this, which is 1 squared, here. So I'm going to add 1 and subtract 1, like this. So then this becomes, now these first 3, if I group them together, it's always x, and then this middle sign, and then the square root of this number, squared. If you FOIL that out, you get that. Plus 9. Right, so that's the form, and now let u equal x plus 1. So then du and dx will be equal to each other. So we come down, this is going to equal, and try to rewrite without using x's at all. Du over u squared plus 9. Now it's in a form that I can use the back of the book. And when I look at my rules in the back of the book, u squared plus 9, this is one of those crazy ones that you might look all day if you don't look in the very beginning. It's rule 13. And rule 13 says it's 1 over a, and the a is 3, inverse tangent of x, which is now u, over a, which is 3, plus constant c. And then this is equal to 1/3 inverse tangent, u is x plus 1, and that's it. Does that answer your question, Joshua? I think that was your Josh?
Yeah, thank you.
You're welcome. And then we had another one, 24. And I can just write that one up. Here it's kind of short. Okay, so I gotta use the rules in the back of the book, but there's none that look like this. They don't have e to the t inside a square root in the denominator. So I'm going to need a u substitution. The natural one seems to be e to the t, but I don't know if this is going to work. We'll just try it. And excuse me. I'll often go down dead ends when I try things. But du equals, you get the derivative of the t is e to the t, and then du dt, multiply both sides by dt. So if I did this, I'm going to get square root of 1 plus 4u. That looks nice. But here is you can't just substitute dt for du, because this is how they relate. So what I can do is solve this for dt is du over e to the t. Now I'm breaking a rule here. I'm supposed to not use t's at all. But if I eventually get rid of that t, it's okay. And then I would say, that e to the t is really u. I'm going to make that over 1. And then I'm going to come down here. I'm going to integrate and copy dot flip. So the bottom one flips over. So I just get du on the top and both of these things in the bottom. Like this. And now that seems like I have a chance to find that in the back of the book. So, does anybody see a rule number for that one?
It's 89.
Not coming through clear, Union. Can't hear you.
It's 89. Number 89.
All right.
Yes.
89, you bet. Rule 89. All right, and I'm going to leave the rest for y'all there. Okay, and all right, there's also a question 21 and 30, but let's do today's lesson first and then come back to more questions as time permits. And let's go to improper integrals. This is kind of a fun section. Alright, so problem number, I think it was 3 in the practice quiz. Yeah, is our introduction to this idea that if you do something like integrate across a vertical asymptote, that's a big no-no. You got to realize that there's going to be a potential for infinite amount of area here. And we're going to do part 1, infinite intervals. So it's more clear that infinity is involved because you see it right in the integral. Alright, so problem number 1 is the integral from 0 to infinity of e to the negative x dx. Now, here's a graph of e to the negative x. It's, you know, when x is 0, you get 1. And the further right you go, the closer it gets to the x-axis. So the x-axis is a horizontal asymptote. Alright. Is the shaded area finite or infinite? Now, I don't want you to think about this too hard. Just see what your intuition would tend to lean towards. Does my intuition lean towards I'm going to get an infinite amount of area here or a finite amount of area? And everybody go to the main text channel and just type one of those two words, either finite or infinite. If your intuition, now if you really don't know, just grab one. But grab one of these two. Force yourself to make some kind of guess. Finite or infinite. Okay, type it in and go ahead and hit enter. And let's just take a brief gander here. Alright, so there's a lot more infinites than there are finites. A few finites, but mostly folks are saying an infinite amount of area. Alright, now this is the ancient Greeks had this very strong intuition that if you add up an infinite number of things, you always get infinity. And in fact, they love these things called Zeno's paradox, where Zeno's paradox was that motion is impossible. Because suppose you have an arrow that you shoot towards a target. Here's your target, here's your arrow coming towards your target. Is that Zeno said, well, first of all, it's got to go halfway. And then it's got to go halfway again. And then it's got to go halfway again. And it's always going halfway, and there's an infinite number of halfways. An infinite number of distances that you're adding together. And so he said, so it can't ever get to its target. And we now know that you can add an infinite number of numbers together and get a finite result. Because you take any distance and you cut it in half and keep cutting it in half like this. It's like we also say the frog who's jumping to this wall. And the frog always jumps halfway. He's very conservative. Doesn't want to get smacked by the wall. And he always jumps halfway to the wall. He winds up getting infinitely close to the wall. And it's the same as the sum of, suppose he was 1 foot away. His first jump was half of a foot. The second jump was half of that, 1/4. The next jump was 1/8. And this is an infinite sum of positive things, but clearly that infinite sum gets closer and closer to 1. Now, people dispute whether this should be an equal sign, because it never quite gets to 1, but it gets infinitely close to 1. And similar things are happening here. If there's, the ancient Greeks would have jumped right away and said, oh, there's got to be an infinite amount of area, because it, keeps going further and further to the right. But we know better than that. We can get finite areas on this. But it's kind of interesting that we had a lot more people go for infinite. I think it's a kind of an instinctive human response that if the region goes out forever, that the area seems like it's infinite. All right. Now, let's look at this integral. How in the world could you do this integral from 0 to infinity of e to the negative x dx? And I'm going to open up the floor and give anybody an idea. Now, give room to have an idea. How might we try to use calculus techniques to come up with this result?
You can use limits.
Why would I use a limit? Is this Josh?
No, this is Matt.
Matt. All right, Matt, tell me what you're thinking. Use limit how?
So we know that we can't really plug infinity into the equation, but if we let it approach infinity, we could get a number to use.
Ah, so what do you mean approach infinity? Should I do this integral like this, 0 to 100, and then do it again, 0 to 1,000, And keep doing it with bigger and bigger numbers and see what is happening? Is that what you're saying?
No, I thought instead of like having infinity for the
Okay.
the top
Mm-hmm.
constraint, we could like use a variable and just say, like the limit as like x approaches infinity of the integral from 0 to x of e to the negative x dx.
Okay, all right. Great idea, Matt. Now, if we use x, though, we're already
Yeah, maybe
using
x.
here and here. So it would be kind of confusing if we used another x here and here. What we tend to use is a and b, integral from a to b. So if I'm going to substitute this top number with a letter, let's call it b. Now, what Matt's idea is it's very similar to doing this with bigger and bigger numbers and just see what the results go towards. And if we just keep getting closer and closer to a particular value when we just take the top number larger and larger, we're going to get the same thing, but Matt's telling us to do it more efficiently by just doing this integral. So what we're going to do is replace infinity with, now I had it written down as t. All right, so let's forget my suggestion earlier about b. Let's get my eraser here. Let's put t in that spot. Okay, so replace infinity with the letter t, then take the limit, not and, it's supposed to be as t approaches infinity. So we rewrite the integral. Instead of 0 to infinity, we write 0 to t of e to the negative x dx. And an antiderivative of e to the negative x is negative e to the negative x, because if you take the derivative of that, you have to use the chain rule, give you an extra negative, so you got to cancel that out. And we evaluate that from x equals 0 to x equals t. When you substitute t in to this, you get negative e to the negative t. When you substitute 0 in it, minus negative e to the 0. But e to the 0 is 1, and it has 2 minus signs on it, so we could do this integral up here, but we can't do it while it's got an infinity in there. We just replace that infinity with the letter t, and we get this expression. Now, what this really means is that when I see this, I can replace that with that, because they're equal to each other. This is exactly the same as that. Looks rather different, but it gives you the same result every time. Okay, so thus, when I have this limit as t goes to infinity, so thus, I kind of skipped something in here. Let me put this in there. Thus, the integral from 0 to infinity from e to the negative x dx. That's what we're after in the first place. We say that that's going to equal the limit as t goes to infinity, because infinity isn't really a number. It's more like go bigger and bigger and bigger and bigger and bigger. It's an idea rather than a number. So it's the limit as t goes to infinity of the integral from 0 to t, e to negative x dx. But we know that that expression can be replaced with this one. So then we do the limit as t goes to infinity of this negative. Now this, I should probably show one more step again. Oops. Oh. How come this all screwing up now? Alright. Plus 1. So we're going to ignore this. Is equal to limit as t goes to infinity of negative 1 over e to the t plus 1. So as t goes to infinity, it drives this denominator huge. It becomes giant. But it drives this whole fraction to 0. And that's why this becomes 1. And thus, this area underneath right here not only is it finite, not infinite, but it's a pretty small value. It's 1. This thing drives to the x-axis so harshly that even though it never gets to the x-axis, the amount of accumulated area, it never quite gets to 1. But it gets infinitely close to an area of 1. Right there. This integral is equal, we say it's equal to 1. Now, again, this would be controversial. Some people would say, hey, that you never get to infinity, so you never get to 1. But we're going to use the equal sign in there, but we're going to use it in this liberal way where we say the limit of this expression as t goes to infinity is 1. So thus, this integral is equal to 1. Okay, and that's going to take us to some new definitions. And let me just put the first of these definitions out to look at. The integral from a to infinity of f of x dx is equal to, this is by definition. It's a convenient definition that really works for us. Is we replace the infinity with the variable t, and then we say the limit as t goes to infinity of that. And we're going to pause and take a break. We will start again. At 6:45 p.m. And does anybody need to speak with me for anything before I take my break? All right, see you in a few. All right, I've muted now.
Hey, how's it going?
Great.
All right, I think I swam 35 this time.
Wow.
Somewhere around 27, 28.
Still being recorded. If somebody watches.
Somewhere around 20, 27 or something. I kind of got miscounted. But I really think I did it right. And the big laugh.
All right, we'll start up again. So, another part of the definition is if the infinity had been at the bottom, like from negative infinity to 1 or something like this, then the limit is very similar. We just take t going to negative infinity. And what's putting these two together, you might think it could go from negative infinity to infinity as one t value, but very not that much so not the case. If you have the integral from negative infinity to infinity, f of x dx, you must pick a number somewhere, any finite number that's in between negative infinity and infinity, and then go from negative infinity to that plus from that number up to infinity. And then this one is this. Well, this one has previously been defined as this, right here. So, the reason why we don't allow let me show you. If you tried to do it like this, what would happen is you would get 0 every single time you did this integral, because these two functions would be identical on both halves, you know, to the right of the y-axis and to the left of the y-axis. But one on the left side, it would be underneath the x-axis. On the right side, it would be above the x-axis. And you'd get 0 every time. But they decided that, no, this, working with infinity is tricky. And this is not what they want it to be. Is they want integrals where you can do the two areas. Because of this, if you had this integral the way it's defined, this one, this integral would be what we call diverges, because you'd have to do it in the two halves, the left half and the right half. And you'd get a negative infinite area on one and a positive infinite area on the other, and we don't say that they kill each other off and you get 0. We would just say, and this is what we have at the bottom here, if the limit on the right side of each of these expressions exists and has finite values, we say the improper integral, and these are called improper when they have infinities in them, or, which we're going to see in a minute, if you integrate over a vertical asymptote. We say the improper integral converges. Otherwise, it diverges. Converges means it goes to some finite value. It gets closer and closer to that. Otherwise, the integral diverges. Any questions before I move on here? Okay, so they really both, like if it's something from negative infinity to infinity, both parts have to exist. Now you might get a function like this, that converges. That would be fine, because the left half could converge, the right half to converge, and then this could converge. But the one up here, let me scoot over to the right, that graph would look more like these two things. And if this one diverges, and it does, and this one diverges, then we can't say that when you take equal portions that it's all going to cancel out or something like this. Those are the kind of things that they probably tried to say. Maybe we'd let that integral be 0, but it presents too many difficulties, and they had to be very careful with how they define things to get rid of some of the really big difficulties. So, we have one for you to try. Do this integral from 1 to infinity of that. And I'm just going to give you a couple minutes to get started on it. And make sure you give it an attempt on starting it. Okay, let me have you stop. Now, you might have realized that you want your u to be 1 plus x squared, and then du dx is 2x, and du equals 2x dx. So x dx equals 1/2 du. And then you say, I think I know how to do this thing. And I'm going to go from 1 to infinity. And I'm going to replace this bottom with u squared. And then the x dx becomes 1/2 du. Alright, we keep going. 1/2, and then this is the integral from 1 to infinity of u to the negative 2 du. Which is equal to 1/2, and what's an integral of u to the negative 2? It's u to the negative 1 over negative 1, evaluated from 1 to infinity. Now, we were doing fine, but what I wanted to model for you was the mistake that is typically made by students. You can't do this. This is treating infinity as any other number. It's not. The only way we can deal with infinity is with some very precise rules. And we can't evaluate the integral without doing this. We must go in this direction. You can put the 1/2 first. Let me actually put it later. You must go the limit as, let's say, t goes to infinity of 1/2 integral 1 to t u to the negative 2 du. Before you get the indefinite integral of this and you have to convert it to t's, and then the only way you're allowed to deal with this infinity is by these definitions. And then we get the limit as t approaches infinity of 1/2 times, now we do the antiderivative, u to the -1 over -1 from 1 to t. And I'll pull that 1/2, it's a limit law, the 1/2 can come out. Limit as t approaches infinity of, and even the negative sign can come out. And then it's t to the -1 minus 1 to the -1. Negative 1/2, the limit, t approaches infinity, of 1 over t minus 1 to any power is 1. Now, as t goes to infinity, it drives this fraction smaller and smaller to 0. And you'll get negative 1/2 times 0 minus 1, which is -1, which is equal to 1/2. And that's my answer. We got this integral, but this precise method of converting over to t's or b's, whatever letter you want, but not doing the integral directly into this. Now, students have a tendency, and on exams I tend to see this, they'll keep going with this. Negative, well then pull the negative out front, so let me put the negative out front and put infinity to the -1 minus 1 to the -1, and then negative 1/2, and then they put 1 over infinity minus 1, and then they might correctly say, well, 1 divided by infinite is 0, and so then they get negative 1/2 times -1, and they come up with the right answer, but I take points off. Why do I take points off? You're dealing with infinity as a normal number. You can't take infinity to the -1 power. That really doesn't exist. Infinity is get larger and larger and larger. It's not really a number. And so what happens is students that get into this bad habit sometimes stay in that bad habit because they can still get the right numbers, but they're not using the correct form. You still cannot do this. Not allowed. All right. Any questions? Well, let's keep going. Number 4.
I just had a question.
Yes.
Can you take the limit as soon as you take the infinite integral of infinity to t? Can you use the limit function before you use the u sub, or do you have to use the u sub first?
Okay. We could have a good point. We could have done it in this direction. first thing we could have done was equals the limit as t approaches infinity of 1 t of x over 1 plus x squared dx. You could have put it into the limit form right away, which is not a very, it's actually a pretty good idea because it makes sure that you don't forget to do that. And then you still have to integrate this thing. And then the only way to really integrate that is to do the u substitution. And then to the rest of the problem goes. But that's a good point. I probably really would recommend that. Change it to the right format first, and then do the rest of it. Thanks, Kylie. All right, let's go to number 4. Which is more likely to converge? And now this one, I'm going to have you ponder this for a moment. Visualize those two functions, y equals 1 over x, or y equals 1 over x to the 4. And then go into your group chat and state your answer there, whether you think it's A or B and why. All right, let me call on group 5. Which is more likely to converge, A or B?
We're gonna say A.
And why did you pick A?
My reasoning why I chose A is because because the antiderivative of 1 over x is ln, right?
Yeah.
And then the ln of infinity is obviously infinity, and then the ln of 1 is 0. So then that just leaves infinity.
Okay, so
Oh wait, I thought I said diverge. My bad.
all right, so you're going to actually say that it's B then?
Yeah. I thought I said diverge. Yeah, my bad.
Okay, so converge means, have a finite value that it gets to, and diverge means that, we can't find the value, and you're going to diverge. And one of the rationales you used was interesting, is you were looking at the integral is going to be ln, and then you're thinking of plugging it in. ln of infinity is still infinity. All right, that's a very good rationale for that. All right. Did anybody? I'll open the floor up to anybody. Anybody have another way of looking at it to see which one is more likely to converge?
Our group said B because the denominator grows faster, so it would hit infinity faster than 1 over x.
Okay, so let's look at the graph of y equals 1 over x. When x is 1, y is going to be 1. And so this one is going to look, when x is 2, you're going to be at 1/2. It looks like this. And let's go to the second one. When x is 1, the y is also going to be 1. But when x is 2, you're going to be way lower, because 2 to the 4th is 16, you're going to be 1/16. So this one, it increases way quicker on this side, and it decreases way quicker over here. So look to the right of 1. From 1 on, we're looking at the area. It's a lot bigger area over here than here, because we're coming down to the x-axis much more quickly over here. So which is more likely to converge? Definitely this one. And we saw two different explanations. One was because we know that that's going to be ln when you take the integral. And the other one was from looking at the graphs of these two. Alright. Now, it's a very important result that we're going to look at right here. We need to get this integral from 1 to infinity of 1 over x to the p. And we can do this, even though we don't know what p is. P might be 1, like in A, or P might be 4, like in B. There could be any such thing. But let's just get the result. This is 1. Actually, let me do Kylie's idea before. Change it to the right format right away, which is the limit as t goes to infinity, the integral from 1 to t, and then change this to x to the negative d dx. So then I'm going to take this integral. So this is the limit as t goes to infinity. Now, to take the integral, we use the power rule. So it's x to the negative p plus 1 over negative p plus 1. But I'm going to write that as 1 minus p. That's the same as negative p plus 1. And that evaluated from x equals 1 to x equals t. Now I need to put the x equals in here because otherwise I'll be substituting the 1 for the p or something like this. It's the same as the dx. That's what these values are in here. And then this is equal to the limit as t approaches infinity. When we substitute t in for the x, we're going to get t to the, now it's negative p plus 1, same as 1 minus p, over 1 minus p, minus, and we substitute 1 in, we get 1 to the 1 minus p, over 1 minus p. Now, as t goes to infinity, you're going to get, well, we can factor out the 1 over 1 minus p if we want, and then we get the limit as t approaches infinity, t to the 1 minus p minus 1. Alright, now p is a number like 1 or 4. It's the exponent. So p is not a problem. When we take the limit as t approaches infinity of this minus 1 is not a problem. This thing is the issue. as t goes to infinity, t to the 1 minus p. Well, let's look at this expression right here. We need this expression to converge. Oops. Go forward. T to the 1 minus p needs to be finite as t goes to infinity. Now, as t goes to 1,000,000 and 1,000,000,000 and 1,000,000,000,000, when will this be finite? Well, let's look at it. T 1 minus p if let's look at some values of p and 1 minus p. If p is 0, 1 minus p is 1. And then you're going to be getting t to the 1 minus p would be t to the first. And as t goes to infinity, t to the first also goes to infinity. Alright, so in this case, we're going to say that diverges. When p is, let's say, 1/2. 1 minus p would also be 1/2. And then you would be getting t to the 1 minus p is t to the 1/2. As t goes to infinity, you're going to be taking the square roots. The square root of 1,000,000, square root of 1,000,000,000, square root of 1,000,000,000. Well, you're still going to infinity. The thing still diverges.
Wait, doesn't that become negative though?
What become negative?
The exponent 1 minus 1/2. Oh wait, no, I'm thinking the other way.
Yeah, and when p becomes like 9/10, then 1 minus 9/10 is 1/10. And then you'd have t to the 1 minus p is t to the 1/10, which means the 10th root, t. As t goes to infinity, the 10th root also goes to infinity. Diverges. Now, when p is 1, then 1 minus p is 0. And t to the 1 minus p is t to the 0, which is 1.
1?
Yes. Now, okay.
But doesn't that mean that it just equals 0?
What equals 0?
The limit, as if p equals 1 and the limit approaches infinity, that means...
Ah, yes. We
0?
would have a problem right here, and that we'd get 0 in the denominator. Right here. even though this would not be a problem, this would be a problem. So we're going to just skip this for now. And let's go to something bigger than 1. If p is, let's say, 2. Or even if, let's just make it even, just 1.1. Then 1 minus p is negative 0.1. And t to the negative, no, to the 1 minus p is t to the negative 0.1, which is 1 over t to the 0.1, which is 1 over t to the 1/10, which is 1 over the 10th root of t. Now, as t goes to infinity, the 10th root of t also goes to infinity. But now it's in the denominator, and this one converges. Because this portion will go to 0. And so, summarizing all this is that if, let me make it a little smaller. If, hang on just a second, I'll be back. Hey, Joan, sorry, we can hear you. Just telling my wife. She was coming through loud and clear. So, if 1 minus p is less than 0, because that's the exponent. We need the exponent to be negative. And then the original thing from 1 to infinity of 1 over x to the p over x to the p dx converges. Now, let's solve this. Subtract 1 from both sides. Negative p is less than negative 1. Divide both sides by negative 1. And when you divide or multiply an inequality by negative, you have to invert the sign. And so then it becomes p is greater than 1. So this is the real thing. If p is greater than 1, then this integral converges. All right. So this p, x to the p, is one that we'll see quite a bit. And when we see it in this one, it turns out that this one diverges. And this one, as we had speculated, this one converges. And the higher the power of the x, the more we like it, because the faster it zooms in towards the x-axis if it's in the denominator. Okay. Any questions there?
You put in your notes that if 1 minus p is less than 0, it converges. Do you mean diverges?
No, if 1 minus p is less than 0, that means the exponent here is negative. And that's what we needed. It was a negative exponent for it to converge. So converge is the correct word.
Okay, so both of them converge?
Yes, they both mean the same thing. 1 minus p is less than 0 is the same thing as p being greater than 1.
Oh, okay.
Because we just solved that inequality to get to this. So, and that's also consistent with when we were plugging in numbers. If we plugged in numbers that were smaller than 1, it diverged. But as soon as we plugged in a number that was bigger than 1, it's converging. All right, let's go to part 2. Unbounded integrals. So part 1 was when we saw the infinity as being like 1 to infinity. It was in either the A or the B position. All right, so we're going to look at this example. The integral from 1 to 3, x minus 1 to the 4/3, 1 over that dx. All right, and recall our practice quiz problem where we got an incorrect result because we integrated right across the vertical asymptote. All right, so if we do this one from 1 to 3, the left endpoint, see, I have a graph of this one. The left endpoint is a vertical asymptote. So when x is 1, it goes up to infinity. And when x is bigger, so this is the function right here. Y equals 1 over x minus 1 to the 4/3. That's the graph of that. And we're looking for the area from here to here. Now, this is one of those problems like before where our first instinct might be, oh, that's an infinite amount of area, but it well could be finite if this hugs in there quick enough. It turned out that some of them don't hug in quick enough, like this one. It doesn't hug into the x-axis quick enough, so it gets an infinite amount of area, which we say the integral diverges. But this one zoomed in quickly, so it converged. So we're back over here. Ideas on how to integrate this. And I'm going to open the floor to anybody. Anybody have an idea of how I might integrate this when we've got a problem at this 1? The 3 is not a problem, but the 1 is a big problem.
There's probably a really long way to do it where you could rewrite the function in terms of x, like, you know, write it as the inverse and then integrate with respects to dy from negative infinity to 0.
Oh,
If that, or something like that.
Ah, okay. So you're saying that we could turn this kind of problem into one of these kind of problems where the infinity shows up in the bounds.
Yeah. But I think that that is definitely not the easiest way to do it.
All right. But it's a very creative way, and that's really interesting. That's neat.
I was thinking that if you have x equals 1, then you have a vertical asymptote, right? Which means it goes to infinity, so why not make 1 into infinity or t?
Aha! We're going to replace the 1 with like t, like this. And, right, if we do that, let me get us some more space. We would take this is equal to the limit t3 but what does t approach?
T approaches 1.
Everybody agree? There's something wrong here.
Maybe approaching from the right.
That is correct.
Ah.
Can only be approaching one from the right. If you approach from the left, it's not at all what we want. Not 2.9, 2.999. It's just from the right. So that's how we're going to do these. And let's go to this definition. If f is continuous on an interval a to b, where it's closed on A, open on B, and it's discontinuous at B. For instance, and now this one would be the limit as x approaches B from the left of the absolute value of f of x is equal to infinity. Okay. Then, the way we define this is we replace, if the problem's at B, we replace B with t. The limit as t approaches B from the negative side of f of x dx, if this limit exists and is finite. Okay, so the definition of this is going to be this. We're going to say, oh, it's fine to have one of the boundaries cause a vertical asymptote as long as we replace that boundary with t, and then we don't let ourselves get there, we let ourselves get infinitely close to there. And then part B, if f is continuous on A to B and discontinuous at A, alright, now in this case I had these wrong. This is A to B. Discontinuous at A. Okay, so the problem is at A, and you know this could be going to infinity or negative infinity. Okay, then this integral is defined this way. So it's very analogous to that one. And then part C is if f is discontinuous at some point in between. Now that was the problem we looked at in the practice quiz, problem 3 in the practice quiz. That we were integrating right across a vertical asymptote. Then, and actually both of these integrals from A to C and from C to B have to be convergent. If they're both convergent, then we define the integral from A to B as two separate integrals, from A to C and from C to B. And we have to define it that way as two separate integrals. So, that one that we saw in the practice quiz, way up here, the problem was at 0 would have to become negative integral from -1 to 0 plus the integral from 0 to 2. It's the only way we'd allow ourselves to do that one. Alright. And now let's go back and finish this problem. So, first step is we're going to rewrite this as limit. Limit as t approaches 1 from the right. The integral from t to 3. I'm going to rewrite this as x minus 1 to the -4/3 dx. And then I'm going to actually take that integral. And this is going to be the limit as t approaches 1 from the right. Now, an antiderivative of this. Technically, I'm supposed to use the u substitution. U equals x minus 1. But I can tell that du is going to equal exactly dx. So because of that, I'm going to skip this. And I think I can just kind of guess what the integral is. It's going to be x minus 1 to the -4/3 plus 1, so that's to the -1/3. divided by negative 1/3, which multiplies by a negative 3. And now, yeah, if I check my work, if I took the derivative of this, these negative 3, negative 1/3 cancel each other out, gives you that to the negative 4/3. So that's right. That evaluated from x equals t to x equals 3. So this is equal to the limit as t approaches 1 from positive. And that negative 3, I like to pull that out front. And then when you substitute t in, you get t minus 1 to the negative 1/3 minus, no, 3 was supposed to go in first. Minus 1 to the negative 1/3 minus, and then t minus 1 to the negative 1/3, and then I get that equal to negative 3 times the limit as t approaches 1 from the right. 2 to the negative 1/3 minus, now I'm going to put this like this. And one more time, I'm going to limit as t approaches 1 from the right. This is 1 over the cube root of 2 minus 1 over the cube root of t minus 1. Okay. Now, as t approaches 1 from the right, what kind of values do I get down here in this denominator? The denominator, I get cube root of really, really small numbers if t is incredibly close to 1. And the cube root of a really, really small number is another really, really small number. So this is going to 0. If that expression in the denominator is going to 0, then the fraction is going to, now it's going to positive 0, so the fraction is going to positive infinity. So, what's my conclusion? Thus, the original integral I'll open the floor. Anybody? What do I claim about it? Thus, this integral, what do I say about it? Anybody? If it goes off to infinity.
Converges?
If it went to a finite number, we'd say converges. But when it goes to an infinite number, we say it diverges. When it converges, like if this thing had, if the red line had been 0, then we'd have said it converges to, and we could have actually gotten the result. It would have been negative 3 divided by the cube root of 2. That's what it would have converged to. But when it diverges, we don't say what it diverges to, we just say it diverges. It goes off to either positive infinity or negative infinity, and then we're not interested in it. We're only interested in integrals that converge. If it goes off to infinity or negative infinity, we say it diverges and we're done with it. Yes.
I don't really understand since if t approaches 1 from the right side and it goes to infinity, does that mean that it only converges when t approaches infinity on the x-axis? Like a horizontal asymptote?
Yes. If this t, instead of approaching 1, if it would have said down here as t approaches infinity, then this would have gone to 0, and then we would have gotten convergence. But this problem didn't have an infinity in here at all. It was just this. So this diverges. And what happens then on these is, because we're running short of time, let's jump to number 5. Which is more likely to converge? Now, if we look at the graphs of each one of these, let me get a little more space. The problem is at 0. 0 is a vertical asymptote. And 0, once again, is a vertical asymptote. And what we saw before was, when this was out to infinity as the top number, we preferred the bigger the denominator over here. X to the 4th was better than x to the 1/2 because it would crash down to the x-axis faster. But when the difficulty is not with an infinity up here, but that this is a vertical asymptote, what we wind up getting is, like for instance, if here is 1, if here is 1/2. Let's just put in 1 over 1/2 0.5 the 1/2 power versus 1 over 0.5 to the 4th power. Alright, now when you take this one, 0.5 to the 4th, that's really 1/2 to the 4th, which is 1/16. This turns out to be really large, 16. This one, if you take the square root of 1/2, so let me punch this out of my calculator. I get, oops, 1.41. All right, so this one at 1/2 is not very high. This one at 1/2, it's super high. It's way up. Oh, this just closed out my OneNote. Closed and reopened on me here. All right. Here's 1 and 1/2. It's way up here at 16. All right. Now, at 1, they're both 1. You can see this one goes into the x-axis much more quickly than this one does. This one's taking its time getting in. This one, which one's more likely to converge? This. So we wind up kind of having the opposite situation as before. All right. How we'd actually do these though is we'd have to, just like we did before, replace the 0 with t and do that integral. And let me point out on number 5. Number 5, let's just at least do the setup for this. The problem is vertical asymptote at x equals 0. So we're going to have to rewrite this. Now, it's backwards. It should go from -5 to 5. That's what I'm more comfortable with. So I'd put a negative sign here and go from -5 to 5. That would be my first step. And write this as x to the -2/3 dx. My next step would, I'd put a negative sign and I'd go from -5 to 0 of x to the -2/3 dx. And then minus, I could put a parentheses around this and put a plus if I wanted. From 0 to 5 of x to the -2/3 dx. And then that's equal to 2 separate problems. The limit as x. Now I can rewrite this as 2 separate limits. The limit as t approaches 0 from the left of the integral from -5 to t of x to the -2/3 dx. Now then I would write plus another limit. T approaches 0 from the right. But I don't have to. Instead, I can just put a 2 in front of this and only have one integral to evaluate. Why do I know that that's the case? Because of the symmetry of this graph. When you look at this, you see that's x to the 2/3 power. Think of that's the cube root squared. And you're going to get positive results all the time, whether your input is positive or negative. So the shape of this is symmetric across the y-axis. Y equals 1 over x to the 2/3 is symmetric across the y-axis. So that's why it allows this shortcut right here, and then we can finish the problem. Alright, that takes us through the entire section, and the homework is 8.9, and midterm grades. I entered midterm grades in today, so you can see where you're standing, and you can also just look in Canvas at any time, see your total average, and if you're in the 90s, you're some form of an A. In the 80s, some form of a B, etc. All right. I am going to stop here. Any questions? Anybody need to talk to me individually?
I just had questions on the last homework assignment.
You know what? Let's see if we can get to that. I can do one right now. and then we'll take the rest. We'll see if we can get to that in the future. So, if it's just 1, which one would it be?
Probably number 21.
Number 21. Okay. And for the rest of you, you're welcome to stay or leave, whatever you like. This is 21 from 8.7. Okay, so I'm not likely to find a rule in the back of the book that looks like this at all, but my U substitution, it seems like sine would have to be the case, because if I did U being cosine, then the du would be in the denominator. We can't integrate that. So make it as simple as possible. And then du is equal to the derivative of sine is cosine, and multiply both sides by dx. So now this becomes u squared plus 2u, and then cosine x dx is all du. Now I've got a chance to find this in the back of the book. But if I look in the tables in the back of the book, hardly any of them have this middle term. Maybe one of them might have. So I'm looking. U squared. Nope, I'm not seeing any like this. So what do I do? It's the same thing with completing the square. So
Oh, I thought it was like took a u out, and I did get rule number 96, but I couldn't figure out where the answer said it was a 2 plus x.
Let's look at 96.
Sine of u.
Oh, you're right. Rule 96 would do it. All right. Let's do it. If you take the u out. So there's two ways. We could complete the square. Now we're going to use rule number 96, and then it's going to be, now the b in that rule is ax plus b. A is equal to 1, b is equal to 2, because there's a 1u plus 2. Alright, so it's 1 over b, so 1 over 2, times the ln, the absolute value. It says x, but I'm going to use u, over ax plus b, which is 1u plus 2. And then plus c, and then this is equal to 1/2 ln. Now I substitute u as sine x, and I'm done.
But in the back of the book, it has 2 plus sine of x divided by sine of x.
Back of the book it has 2 plus...
And it has a negative sign in front of the 1/2 as well.
Say it slowly again.
The answer is negative 1/2 ln of 2 plus sine of x.
Parentheses.
The absolute value.
Two plus sine of x.
Yeah, over sine of x.
Over sine of x.
Yeah, I was just wondering why it was opposite from what it said.
Okay,
Is there a different rule?
now this is equivalent. Well, let me show you. It's just when you have ln's, there's those properties of logarithms can come into play. So this negative sign is the same as -1 times 1/2 times ln of this. Now, properties of logarithm is this can come up to there. So this is the same as 1/2 ln absolute value sine x plus 2 to the -1 power. Now, and what's the -1 power? It reciprocates.
Oh, okay. I was. Okay, that makes sense.
So they probably didn't do this stuff. They probably just did it in a little bit different way, and they came up with that. But we can see that they're equivalent this way.
Okay, all right.
All right. All right. I'm gonna stop the video, and I'll see you all on Wednesday.
Thank you.
You're very welcome.